I want to appreciate everyone and wish everyone the very best in this part of this particular semester. I recognize the extraordinary times that we are in, and I call for every one of us is patience, understanding, and let's work together. We'll be able to achieve the very best. If this can help you to appreciate the circumstances, I want to talk about, you may have seen it on our university website, that Sir Isaac Newton, whom you are all very familiar with, he made a discovery of the famous laws that we actually use now during extraordinary times, like the extraordinary times we are in, by making the best of the challenges that he found himself in. So the question then we ask ourselves is, can we also make the best of the time that we have, so that then we are able to come up with something, so that when we in future we reflect back and actually say that indeed we didn't actually surrender. I think the whole thing here is no surrender, that we can actually do something with it. And all our good instincts and best attributes, we hope they come handy in what we want to do. Having said this, I recognize the various expectations and the various, challenges that may come along, but I believe we will be able to stand up to these challenges. We'll be able to assist one another and be able to pull through this. And remember from our motto, this is when our motto as a university will come handy, that may we all be one. See, may we all be one. And we must live that motto and the virtues that are there as exposed in our university virtues and the policy documents. So I expect us to be the shining light where there seem to be, desperation. We can't actually lose. So having said that, I know we've not met some of you. This is the first time perhaps we are going to interact. So I am Vincent Umenga. I think from the timetable, you've seen my name. So now you can connect the name to the voice and also to the face. If at all you've seen me within the corridors of Strathmore. So I'll be taking you through this course that is computer simulation and modeling. It's an interesting course. I know most of us have various expectations about the unit, and there are various fears. What is this course all about? Just to let us have a feel, I want to request any one of us to say, what do you expect? What do you think is this unit all about? And what do you think this unit should be? So I want to request any one of you to raise your arm and actually be able to say something. Any one of us. We want first to actually appreciate what we have. We try to see what is it. I believe in, you see, if you are going to a market, there is that expectation. So what is it that, yes, you have come here, what do we expect, and how do we, ensure we attain that? So if you won't mind, then I can ask Amani Newton. And in fact, the word Amani means, good. Amani Newton, can you say something? You unmute your mic and say something. Yes, please speak a little bit loud. Yes.
Um, for me, I expect to learn.
Yeah.
Uh, okay, you caught me by surprise, but what I expect most is to learn something new.
Okay. Thank you, Amani. Thank you. Um, Yasin Ali. Yasin Ali, I see you. You can say something.
Okay, so my expectation is actually to have an open mind and to get to learn a lot throughout the semester. Yeah.
Great. Thank you. Mine is to pray for God's grace and the patience and to grant you all your wishes. So thank you. And now I want to share something on the screen. That is the course outline. What I have prepared and what I hope we'll be able to achieve together. We'll achieve this together. So, as I've said, the course is computer simulation and modeling. So the aim, the purpose, why did the university and by extension the faculty consider it important to have this particular course? So we anticipate that by the end of this course, that the learner would have the skills and the competencies. You note something here, the skills and the competence. Now, skills is like the knowledge. Competence then is that ability to use the skills to model and simulate real systems. So, meaning, this course is supposed to take you from that element of not being an abstract person, but to being a doer that you can actually be able to do. And you're going to simulate real system data. Example, you look, basically I want now to say, what is this real system? A real system, I look at a real system like, let's look at what's happening right now in the COVID-19. And I would be using this COVID example extensively, the COVID-19 pandemic. What's happening around it, we call it a system. By definition, a system, we say, is an interaction of various components or various entities, interaction of components or various entities. So you see there is data being generated in terms of who are infected, who are recovering, who are succumbing, and all these things. So when we look at all this data, we say, can we use it to actually come up with a mathematical way of actually communicating this? Or can I actually come up with a way in which I can communicate it using maybe even a diagrammatic representation? So you see, therefore, for you to do that, you need the theory, which you are saying the skills. Then you need now the ability to use those skills in order to come up with this. And the whole aspect here is that you need to solve a real problem. So this unit is more focused on solving real problems, issues that are there in our society. And therefore, as we go through this course, I want you as an individual, not as your friend and what. Whereas, yes, we need to talk to our friends. How have you done yours? But I want you to reflect it on your own setup and actually say, having learned ABCD, how do I apply it in my circumstance? I will be a happy man if you are able to do that. That you can actually, in the middle of this course, you actually say, well, this is what I have been able to come up to solve my problem. Then that will be more important because you cannot solve somebody's problem which you don't necessarily understand more than solving your own problem because you understand it better. That is what we want to achieve. Of course, we'll use what you are saying, mathematical and some other computing tools. Now, therefore, what are the objectives of this particular course? The objective will be the transformation. We want to transform the physical behavior of a system into a mathematical model. A physical behavior of a system, meaning that how this disease is behaving, can we convert into a mathematical model? You have seen everywhere John Hopkins University and others, and even our government saying, oh, we are using some models. So you can see those are the medics or epidemiologists, but they are actually using mathematics. Now, you who is an informatics and a computer scientist, you will actually have more competence in this because you have the ability to turn that mathematical tool into what we are calling an algorithm. Okay, so essentially, therefore, this course converges into what we are actually saying. Okay, can I actually use other sciences that I've learned, like data structures and algorithm, to come up with something which is going to work in a computer? The other thing you will need to do is what we call verification and validation or techniques. Now, we normally say when you come up with a model, you need to test whether it works. Now, the beauty in this class is that we've done IS1, and in IS1 project, you did testing. You wanted to check whether your system is working. And how were you testing? You were actually putting the data and then trying to see the output. And then when the output is good, you were like, yeah, my system is working. I want you to reflect at that system that you developed as being a system which was actually built on some logic, and that logic may have been mathematical or may not have been. Then we will also look at what we call continuous and discrete events. We'll define this, but basically put this way: an event which we know it ends, the start and the end time, we call it discrete. An event that we normally say it's going like to continue, or it doesn't just happen in intervals, we call it continuous. And we will define various characteristics of this. So we want to look at these things, like now, this COVID thing, is it discrete? Is it continuous? We'll be asking ourselves. And then we'll be able to see how we can relate this, among others. Objectives. But what's more important, and what you are going to find slightly different from what your other colleagues have done. So if there is anybody who's actually retaking this unit, so you will see a slight change in the methodology I'm going to adopt in teaching this unit. And therefore, I encourage your colleagues who may want to retake this unit that they need to take this to attend these classes, because for the first time we will actually demonstrate the convergence, because the unit is about computer simulation and modeling. So we must be able to see how does this unit fit into what? Our course. You see, you are an informatics and a computer science. So you are not a mathematician. That is so you are using mathematics, but you apply it in your field. So, and your field is you come up with a program. That's why we are saying there, convert abstract model of system into suitable algorithms. So here is now we say, okay, how do I change this mathematics into a computer algorithm? That is really now, obviously mathematicians may do that, but the person who's supposed to do that better is you. Then the other thing is we'll need therefore to apply now the convergence of other units that you've done. You can see there is what we call AI, and I think you've done AI, but I will focus on a few areas of AI. There's fuzzy logic or fuzzy sets and neural networks. Now, this one is from the machine learning algorithms that you've learned. So because we can't do everything, but we give a semblance that what is there for the convergence of this unit to the other units that we've done. How do we convert these artificial intelligence things into a modeling tool and such kind of things? It's going to be a fantastic thing, I think so. So there are a few prerequisites that we need, and I assume every one of us has done so, has done data structures and algorithms. Now, I want to be fair here. It does not matter whether you got A or you didn't get A in this unit. For me, the key thing is being aware, what do I need? So you see, when you are aware what you need, then you'll go ahead and actually be able to acquire it. So if data structure and algorithms was a challenge for you previously, don't worry, that was then. Perhaps right now, you are a bit more informed about many things, and therefore you can actually be able to crack this. There was things perhaps in some lower levels were difficult, but right now you are like, well, sometimes you get a mess. How was it that I didn't know this? We'll also need differential calculus, and we'll need some concepts of probability statistics. Nonetheless, when we reach some of these, I'll be assuming basic knowledge or no knowledge. So I'll be starting from the foundation. So I will not assume that you know. So my way of doing is that you are to start. So the content is that, but what's important is the way I've structured this. So we start what we call system models and systems. So in this, the whole thing is we want to understand what's really a system and how do we come up with a system model. Here I would also talk about, remember, like an example I'm going to use is a water reservoir or a water tank. In a water tank, we can see a water tank like a system where there is something coming in, there's something stored, and there's something going out. Very beautiful. And what do we normally say about a computer? A computer is something coming in, it is processed, and then we get an output. So there's, so with that basic understanding, anybody can model anything. You see, that I'm going to model something, that I want to see a system as something which has some element of input, some element of processing, and some element of output. Please, you may not remember very many, but have that. That will be the key thing. The next thing that you will be seeing is verification and validation, which I talked about, differential equations in simulation. This one you will guide me, or we'll try to acquaint ourselves. Why I wanted to say you guide me is that I'm not sure if you did some of the what we call ordinary differential equations from what we call first order to second order. Differentiation separable variables, but we'll look into this as we move on. Then look at partial differential equations. Then we'll need some elements of probability and probability distributions. And here we'll be looking at aspect to do with discrete probability and continuous probability. Now, with discrete probability, then it assists us to model discrete events. Continuous will assist us to model continuous event and such kind of things. Then we also will look at the two scenarios. Discrete, an example of a discrete event is you see, like when you go to an ATM machine, that is a discrete event that somebody goes, finishes a transaction, another one goes like that. That's what we call a discrete event. When you go to the other one about continuous, is slightly different. We change and look at examples of continuous systems. But in most cases, most events in the world are discrete. We'll also look at what we call simulation languages. And in simulation languages, we will be keen on the first one that we will be looking at is what we call similar. But of course, we may actually look at C++, which you have actually done in your object-oriented programming. Then the last one is where we use database, AI, and simulation in modeling. So that is basically what we'll be looking at as far as this is concerned. Okay, so that is as far as the course is concerned in terms of the structure. Other things that we are going to look at is the evaluation is going to be continuous assessment, and the project will constitute 50%, and the final examination will be 50%. That brings it to 100. All our communication will be through the email. And at this particular point, I want us to propose module leaders for different groups. Then they'll be able to assist us communicate. Module leaders will only for this particular unit. They will not take the role of class representative. They are for this particular course. I'll be glad if we propose the names of potential module leaders, so that then we can actually be able to use them for purpose of assisting us to communicate. So please, let's propose potential module leaders. Yes, I can see Tinashe. Tinashe. Okay, another proposal. Then Stephen Wanye. Yeah, this is group A. Now Tinashe is for group what? It's for group B. So group B, and then there is Rodi Bakari. Rodney Bakari. Let's agree on one, because I think you are on two groups, so let's agree on one. And then I can see there is Bakari, there is the Raru. So whom do we go by? There are three for group B. Rodine, Edward Urina. It seems in group B we are going to have a vote. So I'm likely to put the voting so that then you are able to vote. So sorry, I've limited the chat for purpose of having some element of control somewhere. So shortly I'll be putting we have to vote, so that then we are able to do we need to vote really? Can I assume that those who have actually managed to say something that I've actually said? Then we go to Miraru. Can I assume that is for purpose of this unit, and we believe they'll do a good job. So can we take it Wanye and Biraru? Raru. Good. Having done that, So then I will then now move into the next part of our discussion now. So that then now we can move into some bit of work. So shortly I'll be sharing the screen so that then we can actually be able to see what I want us to discuss today. In a minute we'll be up. Good. So that is what I want us now to share, that I want us to discuss. So this is topic 1. And in this topic 1, I want us to look at lesson 1. Some of these materials are there. I have uploaded them on the e-learning. You will be able to access. The enrollment credentials were shared. So now, good. So the first topic that I want us to look at is what we call introduction to simulation. So we need to actually note what is simulation. And this introduction to simulation, then we'll be able to note what it is and then be able to see how it works. So then that's the first thing that we want to do. I can see there is a question. Yeah, there's somebody who's indicating that you are not able to enroll into the course. My apology, we have done some limitation. You have to enroll using the enrollment key. I will try to make a follow-up and see whether you got the key, because it was shared using the class representatives. Please get in touch with your class representatives. If you're not able to enroll by tomorrow, I'll be able to see how to sort that out. Yeah, somebody says the key did not work. The key could not work perhaps somewhere. The last letter, it has to be O, capital O. If you put another, it can't work. There's an underscore, and then followed by, capital O. Just try, and then let's see how it will work. Just try. If it doesn't work by tomorrow, we'll be able to sort it out. Good. So in this, therefore, by the end of this lecture or lesson, you allow me to use that word, I want you to check whether you can be able to explain what is simulation. Number 2, can you be able to identify or list areas where simulation can be applied? The next is, can you be able to discuss the advantages and disadvantages of using simulation or conducting simulation, among other things? I want to encourage those who are making comments on the screen to avoid that, because nonetheless we'll be sorting out this one in the next subsequent. This will not occur, but I want to encourage those who are doing this to desist, because you are not being helpful. Yeah, I intend not to track the person doing it. I intend that we actually desist. If you want to ask, you can raise your hand. I'll be able to see, and then I'll give you a chance. I think that will be much better. Then explain the difficulties associated with simulation and discuss circumstances under which simulation will be important. Having said that, so let's discuss. So the starting point here is the first thing, as we have said there, is to understand what is simulation. There are a number of definitions that can be attributable to simulation, but one thing that is agreeable is a way of defining, or coming up with a real world occurrence, putting it in a manner that will be possible using mathematical models. In other words, is the conversion of what's happening in the world to be mimicked or to be imitated using mathematical manner. That's why we say it can be defined as a technique of studying real-world dynamical systems by imitating their behavior using mathematical models of the system implemented on a computer. So what does that mean? In simple terms, you see, if we say 10 plus 5, we know it's 15. We actually do this. We can do it. But we can also use a computer to do it. So the mere fact that we are converting that which we can do intuitively to use a computer to do it, then we are actually saying we are simulating the real world. Or put it this way, if you wanted to take temperatures, and this is very important, temperatures of a patient, like what has happened. I think you have seen the creep in Mombasa County. You want to record the temperature of the patient as it's happening right now, not a patient of people. You can automate this such that now you can actually be able to do this in a remote manner. So in other words, you are converting systems which ordinarily work in a particular way, so then you use a computer to do it using mathematical underpinning. So how then do we come up with this? Meaning that there is something that is important here. Behavior, please note that, behavior. If you go to your computer programming, we talk about if you're writing a program in object-oriented, we talk about attributes. Then from attributes, which again we can also call them members, class members. Remember that? Then in the class member, we move to the next level. We say there is a method. A method is also seen as a behavior, isn't it? So what we are saying, therefore, what's important for you to come up with something to simulate a system is understanding the behavior, understanding what that method, rather that what that entity does, because a behavior is attributable to an entity, and an entity is an object. I think I need to put that one in a chart here. So I'm saying we need an entity, we need to simulate. In this case, an entity, let's call it an object. Okay, and an entity, we will then need, if we have to come up with it, we will then look at the attributes of that entity, and these attributes of that entity will give us, remember, the characteristics. But more importantly, then from there, we then want to ask ourselves, what are the behavior? Okay, the behavior. And in this particular case, in the context of what you have actually come up with, behavior gives us what we call a method, meaning that you cannot be able to come up with anything until you understand what's the entity, what is the attributes, and what's the behavior. So if we have this, then we try to actually say now, in reality, this is how the entity behaves with these characteristics, but then transfer that one into a mathematical model, which you can implement in what? In a computer. And that is what we call simulation. The next thing is, where do we apply this simulation? There are a number of areas where simulation has been used. The first is it's used in manufacturing. In manufacturing, I can give an example here. Before you, like what you have actually seen happening in the pursuit to get a vaccine for the current pandemic, you've read or you have listened to or you have heard that ordinarily a vaccine development will take almost 10 years. Others have taken eternity anyway. But because of simulation, or the power of simulation, they are able to do what we call replication. What does that mean? It means, and this is very important for us to be able to then contextualize this importantly. You see, in vaccine development, it means you take the vaccine, start doing a number of experiments, and this a number of experiments will take time to be able to get an outcome, because now that's when you are putting in the real environment. So that time may be longer. But now with the simulation, you are actually saying you will actually be able to you create those environments, and then you fast track this thing. So it has actually enabled the development of this vaccine in a more in a faster way. Also, in manufacturing, there's what we call prototyping, which is more or less what you remember. Also, you've done prototyping in system development. In prototyping in manufacturing, it's like you want to kind of mimic a real product using, a virtual environment, something like that. Huh? Computer systems, we, like most people will do systems or computer applications and then try to test them using data which is not necessarily from the place where it's going to be used. So in that particular case, you are actually saying you are simulating. You are using information or data which relates to a similar environment. So we call it that you can actually do that. Other things is what we call e-business or workflow systems. In other words, you are coming up with an application, and sometimes you do not know how it's going to work. So you try to create an environment what you think, that is how that environment is going to work, and then try to test those systems and see how they are going to work, among others. Allow me not to go into all these other sections, but these are some of the areas where simulation has been applied. Also in research, it has been used in agriculture, and everywhere. Literally, simulation is used in a number of circumstances or areas. I'll pause there, take a question if there is any. You can raise your arm, then I'll give you a chance to ask. Yes, there is a question: is simulation purely used for purpose of prediction? That is from Wangare. The answer is no. You are right that simulation can be used for prediction, but it is not the only use. As we are going to see later on, we can use simulation to predict, but we can also use simulation to do other things. For instance, analysis. As we will see, there are a number. In fact, I think in chapter 2 or topic 2, we'll be able to see some of this. Any other? Okay, thank you. Let's carry on to the next page. The next is, what are the advantages of simulation? We say simulation of arbitrary model complexity. What it means, arbitrary complex, aspect. An example, I want to give a very practical example here. If you wanted to see when people are coming up with a car and they want to check on the stability of the car, whether this car is going to be stable on the road when it is moving at cruising speed. And I'm not saying that you go try that one. Some of us here might go try. That would be very suicidal. Anyway, you will see why it is suicidal. So what happens is that before the designers conclude that the maximum speed this car can move is 180 kilometers per hour, what they do, they actually simulate. Now, when they simulate, you can be sure, I come from that field of engineering, you can be sure many vehicles or many designs could have, they may get spoiled because they must actually drive. They must assume that suppose this vehicle is driven at a speed way beyond 180. What happens? How does it, skid? What's likely to happen when it moves at 250? So you can imagine, before you settle and actually set all the necessary mechanics to ensure stability and other aspects to ensure that this thing is going to move, that's highly complex. So otherwise, so many will crash. So what therefore happens is that they actually use simulators, whereby they actually say, suppose we design this, in a virtual kind of an environment, and then they try to make that thing move that fast. What happens? Then they are able to analyze, and then they are able to say, oh, okay, yeah, perhaps this will not be okay. Let's change this. Then it tests like that. That's something that is done. That's what we call arbitrary model complexity. The other thing is circumvent analytically intractable models. What become analytically intractable models? Let's look at it. Yes, there is a question. Yes, the question is, how do we determine model complexity? A good question. And we want to look at this. Model complexity is determined by a number of criteria. In fact, we'll look at it, I think, in lesson 3 or thereabout. But just to mention this, the complexity of something is also determined by the number of iterations that you must go through. Let me put it this way. You remember in algorithm analysis, if you may recall, we talk about different algorithms, others which are simple algorithms, which sometimes we call them constant algorithms, and others which, becomes highly, computational. And so the more the computations they are, the more the complexity. In other words, we are actually saying the more, can we say the more iterations you want to do, or the more challenges that you must come, or rather overcome, in order to come up with something. That is how you can look at the complexity of this. But we'll be able to keenly look at other aspects of analyzing. In fact, it's in chapter 2 where we are going to look at analysis of the model, where we are looking at the verification and the validation of the model. One of the aspects we will be looking at is this element of complexity. But simply put this way, that what makes a model complex may be, number one, the number of algorithms that needs to be, to be computed. Then the other thing is the amount of task that is going to be done. The amount of task that is to be done is also an element, which then now takes us back to measure of an algorithm is as a consequence of time complexity and space complexity. So without taking you back to data structures, but have that what we call time complexity. Time complexity comes the amount of time taken. Then space complexity, we also look at the amount of space or resources that you are going to look at in order to accomplish this. So when you have all these things being too heavy and a bit of a challenge, then we say there is a complexity in terms of the model, which then boils down to what I've actually given an example, that if for instance, for you to be able to arrive at that this is the right model, when you see the cars, the shape they take, there are so many things that has gone through it until they agree that this is the right shape, so that then you are able to ensure the better movement of the vehicle, the stability, and the other aspects of which accompany the comfort, and among other things. It's not something that someone decides and actually say, oh, this car must move at this. They actually make sure that indeed it is tested and it can actually move like that. Of course, the roads notwithstanding, Kenyan roads are not designed for the 180. So I should have warned everyone there. I hope that answers your question. There is AI. This was AI. I don't know the other name. I hope and encourage you to write in future your full name so that we can actually be able to know each other. Circumference analytical intractable models. This is an important element. For instance, intractable models. Intractable means that you can't reverse. Just reflect on when you are. In fact, I want to. I hope everybody is seeing what I'm holding. This is a glass. Now, this glass, when they go through what we call quality testing, some are subjected to what we call extreme testing. And one of those extreme testing is you actually, if you are saying that it's, if I hold it and actually leave it to fall, that it can't break. So if you do such kind of things, Just imagine how many classes you will actually be able to spoil. So what system modeling as assistance is to imagine that if you put various components together and then subjected them, how would they behave? You simulate and actually get to know, okay, it is this particular level. So you would then now move into production. Let me go to a complex one. Is, for instance, if you are testing like before they come up with what you have actually seen, vaccine or medicine for treating specific diseases. Remember, if they start using it on human beings, there are so many tests that are done until there are those which fail and others are very fatal. So what happens is this: they actually do this simulate environments in in a laboratory. Better still, let's look at what I think you saw in the video, perhaps you can check KU. They were trying to ventilator, and you had them say that they come up with a prototype. Now, prototype is a model, really. Now, therefore, you can see they went and actually tried to put that thing into a human being. You can see if it has an error, you can see the challenges. You can't retract what goes there. So before that thing is used in human beings, it must be simulated and tested in a simulation lab. There is what we call facilitated what if and sensitivity analysis. Sensitivity analysis, I'll explain this. What if you know what analysis from your algorithm is, it gives you a way of checking. In other words, it gives you options. If this, what do I get? What is this? Now, to check on various alternatives. The simulation gives you to get alternatives, not one, which ordinarily could have been like, if you didn't have the ability to test on what if, then you just move straight and actually say, this is it. And therefore, you don't have alternatives. It's like saying this. You've seen, maybe I can use an example of, how do you call it? Radio stations. You tune, you change. So meaning that they must have simulated and actually said, if we change this, then this can actually work. That's how it works. Now, what we call about sensitivity analysis is this. You have always actually heard people say that this thing is highly sensitive. A machine being highly sensitive. What it means is that it can test even the minutest value. Sensitivity analysis is where now you are actually saying, okay, I have come up with this system that when I put, various amount, of values, how does the system behave? How does it behave? Does it give result? Does the result increase? Does it go down? An example of sensitivity analysis that I think most of you could be aware of is look at how the market performs. Market analysis, for instance, right now, various stock exchanges are really down. Why? Because they are sensitive to, the happening. When somebody says, well, this epidemic is going to, to be there for many years. So somebody will be like, oh, so what do I do in order not to lose my, money? So meaning that something small makes something, respond differently. That's what we call sensitivity analysis. Now, how does the system respond based on the various inputs that go into it? And we will be looking at sensitivity analysis, particularly as an element of validating. You validate your system by subjecting it into sensitivity analysis. And I will be demonstrating how I did for one system that I was developing not far long ago, to be able to see that. There's a question. Circumventing analytical and interactive model is minimizing the testing on real-life model by testing through simulation. Gabriel, yes, it's so to speak. That is true in the context when you are dealing with what we can say natural science. But of course, you can do this that we are calling intractable also in actual manufacturing and other similar circumstances. You are right. Now, the next one, I want to take the last bullet and then we'll take a break. I want to give a break of 30 minutes for most of you to take a bite. Then we'll convene for a very short chat before we call it a day. Now, the next one is building a model can lead to system improvement, and a great understanding can be used to verify analytical solutions. So what this means, for those of you who will be going into the advanced courses, you will get to understand something, particularly when you are in management or such kind of things. You'll get to understand that if you want to change something, you need to give people reassurance that this change will lead to either improvement or ways in which you will do something better. So, and the way to do it, because now you see when you are telling people, if we change this, it means you have not changed. So what does that mean? It means you are creating a scenario so that the people are able to see this scenario will take us there. What is that? That's the simulation. And therefore, it becomes something like in management, you will want to use so that you don't go to tell people that I want us to change this without actually giving people a reason to believe that a change is going to be what? It's going to be good. I'm sure you've always heard people say that change is what people change rather fear most is change. When change is brought in that manner, which is very, can I say, in a manner that is abrupt, then it defeats the purpose. But what happens is that if you simulate it and actually say this is the current way of doing things, takes us here. Now, the new way of doing things, if we change to A, B, C, D, we reach here, then people will be able to have a buy-in and perhaps there will be improvement. So something like that. So I'll pause there, take any question before we take that break that I've indicated. So any question before we take a break? Yes, there is one. Yes, Isaac says, is there an e-learning platform of this unit? The answer is yes. There is an e-learning and the materials are there. I actually indicated that perhaps it could appear a number of you are having challenges in enrolling. I will encourage you to try. If you are unable, then in the next lecture, I'll be able to show you how to sort it. Yes, there is an e-learning and the materials are already there. Not all of them, I'm building them too, but they are there. The next question by Helen is the session being recorded? The answer is yes. For purposes of those who might be having challenges on the audio side, we are actually recording and we shall be able to upload the same also in the e-learning. The next one is, thank you, Isaac. The next one is Omando. Is it possible to break after the class instead and rather finish the class earlier? Stacy, I really would have wanted to do so, but the reason is this. I want to give, there could be one who wants to stretch instead of sitting for 3 hours. It's not helpful. different people are in different circumstances. Allow me just to break this for now, but I don't know whether it will work. So that then we can actually resume later. I think it's not that this. But if everybody is okay, which I do not, I won't mind going up to for another 30 minutes and then we conclude. Does that work? Considering what Stacy is raising, I hear Matata and everyone else seems to be saying yes. Oh, great. Let us not vote. So we are going to go that. I think there is also John saying we need a break. John, Mutanya, what do we do here? Let me now be a big brother here. I request we take a break of 20 minutes. That is not too much for people to even, others may want to go to the washrooms and actually be able to reconvene. 20 minutes would not be too bad. My apologies, Stacy and colleagues. So for the purpose of others, let's take that short break. 20 minutes we reconvene to finish the class. Thank you. I will want to give others a few minutes to. So welcome back, as I said. Again, could appear that there is somebody else who was doing some things here. We'll be able to track that one. I think I indicated that for purpose of harmony, we shouldn't. We only use this for what is expected. I can see a number of people trying to do what's not necessary. Therefore, we'll be able to. That is not very helpful. So the next thing we want us to look at is what are the advantages or disadvantages of simulation. The first one is that it only provides what we call estimations of a solution. So it doesn't necessarily give you accurate. And therefore, when you work with estimations, it means there is some element, there could be element of errors, or there could be some accuracy in it. So there is element of uncertainty, so to speak. The other one is only solves one parameter at a time. And that's where we talked about sensitivity analysis, meaning that because we are talking about input and then process and then output, so meaning that you will take one input at a time. And that's what we are calling one parameter at a time. Now, it's very possible you may put many parameters at a go, but then we are actually saying at a time. Now, the other thing is that can take a large amount of development time of computer. Yeah, remember, here you are testing a number of things. I'll say the example I was giving of KU, it requires a combination of many things to be able to come up with something that you can simulate. So it needs, so there's resource utilization. The other thing is now, what are the difficulties in simulation, which is a continuation from the disadvantage kind of. Now, the first one is that provides an individual, provides only individual, not the general solution. What that means is that if circumstances change, then you are like, you must go back and actually recreate a system in a different environment. So that brings in what we are calling challenges. You need so simulation might not be versatile enough, might not be applicable in generality. Okay, the manpower and time consuming, which is more or less like a disadvantage, and therefore by itself becomes a challenge, difficult. Sometimes you may not have the expertise in this. As I'm going to demonstrate later, I think I'll give an example. And you can actually Google perhaps and read a little bit on this. It's what we call system dynamic modeling, SDM. Now, system dynamic modeling is commonly used in what we call for modeling. It's a science of modeling what we call complex interplay of systems. So the expertise it requires somebody who's versatile in many fields. So at the end of each all, therefore, you see a simulation environment will require a lot of manpower to be able to come up with something, and hence that becomes a challenging task. The other thing is computer memory and time intensive. That is resource, and I think we talked about there the element of being intractable and the kind of things. The element of complexity, when I was talking about time and space complexity, that's where it comes. You can see space complexities, computing memory, time intensive or time complexity, then brings in what we call it time complexity. So those challenges or difficulties are there. How do you balance them? It's a question of what we call optimization. And the problem of optimization, as you may read or may have come across, to optimize an algorithm, you need to consider so many things. And therefore, with that also comes challenges associated with what we are calling the algorithm or the simulation itself. Now, the other one is hard to interpret results. So sometimes you see this result may be given in an abstract form, unless you have, because it's not real. So you want to interpret it in a real environment. So when you try to interpret something which is from an abstract sense, and then you try to put it in a real environment, so there will be that element of variability. And then also can be expensive, as we have indicated. There is resources that one will need to work on. Now, which are the circumstances when a simulation is required or important? Are there circumstances where you need simulation? The answer is yes. The study of internal complex systems, biological systems. An example is what's going on currently. Any biological systems will require what we call complex, because it touches on existentiality or the existence of organisms. So you don't want to study things by killing them. You want to study things first to understand them before you deploy. So in such a circumstance, you need simulation. Optimization of an existing design, or for instance, routing algorithm, assembly line, etc. I do not know examples of algorithms you studied previously. Routing algorithm is one of the algorithms that you can study, and I think there's a study so as one of the students, you may read it in our university library. Like if somebody wants to go to, let's say what you are looking is somebody who wants to go for vacation, or for, can we say for, not vacation really, to tour. The question then one would ask, what people consider is, which is the shortest distance, which is the route which will give me the best features that I can actually be able to say, which is the route that I can actually kind of get value for my money. So when you look at all these things, it's like there are so many things that you need to compare. So you see, to answer that question from a practical sense, it means you will need to test all those routes by driving through those routes. that may be expensive. So the only alternative you have is to simulate. If you know the route, let's say you want to go, let's say you want to go to let's say Northlift. Northlift in Kenya, that's the Rift Valley, the Northlift part. You want to go and actually, to tour, to enjoy yourself. So what you need to do is to get to know the routes that will take you to the North Rift, the distance, and then try to look at the features that are along that particular route. So when you have that, so what happens is that you simulate. You sit behind and actually simulate and actually say, suppose I use this particular route. What are the features I'm going to use? What time am I going to spend? What benefits am I going to get? Again, you go another one. In ordinary circumstance, what one will do is that you will drive through this, incur the cost, then come and actually say, after all, this is the best. So you see, you can actually use simulation not to incur that expense. That is what we call optimization. Assembly line is more or less the same. For those of you who happen to come from Thika, in Thika there are two, I think, vehicle assembling plant there, and there's another one around Mombasa Road, the one of General Motors here. For those of you who come from Mombasa, there is another one in Changamwe and such. I'm talking about the vehicle assembling plant. What happens is that when people are assembling, when the manufacturers are assembling the brands, the vehicles, they actually do it, they want to do it in a manner that they spoil less things or minimum destruction occurs, so that then they are able to get the best product. Never, I think our government wanted to start local assembling of computers. I do not know how successful that has been, where some universities were given that opportunity to assemble. So the whole thing here, for them to assemble, then they needed to use simulation to check on the best and the easiest way in which they can actually put these computers together, computer parts together, to ensure minimum resource utilization. Examining effect on environmental changes is weather forecasting. For those of you who may have time to read, I think one of my paper might be appearing in the internet. You may find it on weather forecasting. In this, what I was trying to do is trying to look at what we call exogenic, or can I actually say circumstances that are happening generally on the biosphere. Just like you see, if you are seeing human activities, you are seeing other aspects associated with this. How then do we use this to be able to forecast what is going to happen? Which then brings the aspect of a prediction, as asked by one of us. I think it was Ombua. The lady, I think it was Helen. I think Helen asked a question about that. So that's one example in which we can actually use this. So I didn't have to actually wait for it to happen. My model can actually be able to predict, given the circumstance, you put the input, it can actually then be able to predict using some algorithms that we actually be mentioning some of them, what you call the logistic models, which is an extension of logarithmic or exponential kind of logarithmic systems. Now, there's also what we call systems which are dangerous or destructive, like atomic bomb, atomic reactor, missile launching. So these ones, before they go to launch, they actually simulate and try to see this. How does it work? What are the issues that are likely to be? The example is what I gave the vehicles, but the better still is aircrafts. What they usually do, in fact, they simulate before they release. And that's why, My apology, the example I'm going to give, I hope it will not touch any one of us, but it's just an example I'm giving. The accident that occurred in the Ethiopian airspace, when the investigators were trying to investigate, they tried to simulate in order for them to understand what may have happened. So you see, if they were to find what was happened by using, real, kind of scenario, it means they were to fly an aeroplane and then, allow it to crash. That will have been it can't work. It's not correct. So what they do, they simulate an environment that perhaps this is how the vehicle, rather the plane went, and this is what may have happened. And then they try, this is used in forensic analysis and the forensic investigation. For those of you who may go to that field in future. There is also when you want to study important variables, like you want to test in a system. And when you look at variables here, it's even like we are looking at materials in our production. Want to see if I put this raw material, what do I get? How does it affect such kind of things? Testing new design or policies. This is very also in line with what we call in our production industry. Among the many areas, I don't need to go in each, but I think the last one I've talked about it. Simulator can be used for instruction, avoiding trying up or damaging an expensive actual system. That's flight simulator versus an aircraft. So we did that, and many of other areas where it can actually be used. I don't need to really overemphasize. Where you use these things is quite extensive. So that brings us to what I call the end of lecture 1. And at the end of every lecture, that's what you are going to see, which is slightly different. Perhaps, I don't know. This is my way of doing things. At the end of every lecture, you'll be having what you call lecture practice questions. Now, these lecture practice questions are specifically designed to offer you an opportunity to reflect on what we have discussed in a more in-depth way, so that if you are maybe having, you are relaxing at home or under, under a particular environment where you find yourself in, you can actually have a chance to reflect that in today's, there was a discussion and what was expected was this. Then if you are able to answer all these questions, then it means you are actually, you are better, meaning that you have actually understood what we covered. So I encourage you to take this. So because it seems that perhaps the e-learning, I don't know the challenges that are there. I'm going to show you that indeed the materials are there shortly. I encourage you to take a screenshot of this. You can take a screenshot using your laptop or your personal computer, or better still, take a photo of this using your phone. And then this last section, if you answer, it generally captures what we have discussed in today's lecture. There's a question. Yeah. So yeah, that is Stacy. I want to take a moment. In fact, I just want to go there right now. So in a minute, I'm going to log into the e-learning. I check and then I get back to you in 2 minutes also. So I'm going to stop the share so that then I can be able to log in and see this in a minute, please. All right. Now, can you try to enroll those who are able? Let me know. If you again check on the screen, that is actually the what? That is the portal. So indeed, the unit is there. So the first topic is system modeling, what I've actually indicated, and so far this is you know, the first thing that we have actually covered, lecture 1. And so there is lecture 2, lecture 3 as we move on. And then there is chapter 2, which also has a lecture 4. It is. So indeed, they are there. So can you try and let me know? So the next thing is there are questions again. The password Ngugi, John Ngugi, allow me not to share it here because of one or two privacy issues, but I know it was shared through your class lab. I can confirm they were sent to two class representatives. Just if you can get in touch with your class representative, can be able to give you the enrollment key. Allow me not to share it through here because I think there's one or two things that I need to fix on this platform before I can share anything through it. Yeah, Gabriel has managed. So Gabriel Mbugwa, yeah, Hassan has managed. So I expect a number of you to manage. My apology for those I can't share them through here. Then there's a question of how would you record our attendance? Yes, your attendance is being recorded. The application has and this is important to mention. This application is able to record who, and that's why I was saying I can later on go in and see who was doing what and say kind of things. But what's important is use your official name when logging in, and also your official name, admission number, and your group. Please, this will be important. Your official name, your admission number, and your group. You are in group A, group A. You are group B, group B. That will assist us because when you write that, then on the other side, it will be easier for me to be able to capture you correctly. What else? I hope I've responded to all the questions here. Anybody who's having challenges, perhaps the password, contact your colleagues, like the ones I can confirm. There are a number who have managed to do so. So they may be of help to those who are having those challenges. If there isn't any further, yeah, thanks, Motanya. That's good. If there isn't any, yes, Rosanne Odiere was one of the, group members who was given the enrollment key. So Rosanne, please share, and your colleagues will get in touch with you. You give them, not through this platform, please, until I fix one or two things that I'm not comfortable with. So with that, any further clarification from this side before we conclude this first lecture? Should we send our names and admission number? No, what I mean, Hassan, is when you are logging in, you use your names and the admission number and your group in the system when you are logging in. So you log in through your correct but if you have used pseudonyms, then you will need to find a way of sending your correct names to me through the official email, which is v.omenga@strathmore.edu. But I hope in subsequent we'll be able to use the correct one. For those who have used your names as they have, if this is how they appear in the MS, I'll be able to get them this way. Thank you, Calvin. I appreciate. So I want to wish you all the very best. We'll keep improving what you are trying to do. And where we have errors, please be able to point out. We try to improve. As I said, this is new to you. Might not be new to some of us. We've been using the technology, but obviously different groups with different circumstances. We want to improve and help you to make sure that we are all at par. So there's in the Haru, you can give us the module leaders, the role. Yeah, this is very important. The module leaders, before, I hope we settled and I agreed, Stephen Wanye and Biraru will be our module leader. Now, the role of the module leader, they'll be my point of contact as far as this unit is concerned. So the module leaders, please, my email is this one. My email, you know it, I suppose. If you don't, you get it from, you can write to the course administrator, she will give you my email. You will be the one to guide us. The success of this class will be dependent on you. Please be the persons who are going to tell us where we are wrong, where we need to go, and how we need to do things. Yours is to ensure there is order, there is harmony, and there is peace. So please, you will be the one to whip, kind of, so to speak, to ensure that there is discipline. You will be very important, and you'll work hand in hand with the class representatives. The class representatives, you see, they handle many things, but for you, it's only specifically this unit in terms of ensuring we get our classes start on time, ensuring that there is discipline in terms of the class, that if I am in discipline, you tell me. So really, I become a better teacher by actually listening, and such kind of things. So basically, that's what you are actually going to do, to assist us to do these things in a manner that is collegial and satisfactory. Then there's a question at some power issue in Langata, so I was unable to follow the second part of the class. Will it have, like to have the class enrollment key? Yes, Mwambali, I have indicated, yes, the class, the enrollment key is with your class representative. Please get in touch with them. But once I get also the emails of the module leaders that we have appointed, I'll be sharing to them also the credentials, the enrollment key. So if the two, Stephen and Biraru, please write to me, and then I'll be able to write to you, and so you will also be point of contact for the group. So hopefully I've answered all the questions. I want to wish you well, and please keep safe. See you in our next lecture, and thank you.